To navigate, build, and survive, we rely on flat maps. But the Earth is not flat. It is a chaotic, three-dimensional surface of peaks and valleys. The core problem of cartography is mathematical. How do you compress a three-dimensional world onto a two-dimensional plane without destroying the elevation data? Historically, mapmakers bypassed this mathematical complexity by using artistic sketches to simulate depth, rather than encoding raw height data. Take a look at this vintage Cassini map of France. To capture the vast geography of the nation, early surveyors relied on dense networks of ink to sketch the physical terrain. This is a tactical map from the Battle of Waterloo, illustrating a specific technique called hachuring. These short, caterpillar-like marks are drawn strictly to indicate the direction a slope faces, a visual shorthand militaries relied on heavily to spot high ground. During the Renaissance, artists like Leonardo da Vinci experimented with an alternative called hill shading. By mimicking how sunlight falls across a physical surface, the steep slopes are darkened and the flat ground is left entirely unshaded. Both hachuring and hill shading fail the basic requirements of engineering. They create a visual illusion, but they contain zero quantifiable height data. You cannot look at those shadows and calculate how deep a trench needs to be, or whether a train can make it over the pass. To move from sketching the landscape to actually measuring it, cartographers abandoned artistic rendering in favor of a precise mathematical language for the z-axis. Before you can measure the height of a mountain, you need an absolute baseline that applies equally everywhere on Earth. That baseline is mean sea level. This diagram shows how surveyors carry that sea level baseline inland. They mark specific, discrete locations with exactly measured elevations, called spot heights. It's a literal scattering of numerical data points across the map. You can't always drag measuring equipment up a sheer cliff. Instead, surveyors use trigonometry. By measuring the angles from two known, accessible points, they calculate the exact height of a third, inaccessible peak from a safe distance. This chart illustrates the result: triangulated heights. They appear on the map as small triangles next to the calculated elevation numbers, anchoring the highest peaks to the data grid. To ensure these measurements aren't lost, the data is physically bolted to the real world. Surveyors carve or embed permanent markers into stone, bridges, and buildings. This is a benchmark from the U.S. Geological Survey. It permanently fixes the abstract map data to this exact physical latitude and longitude. But raw data points are isolated. A scattering of numbers tells you the exact altitude of a dozen specific rocks, but it communicates nothing about the continuous shape of the land between them. To visualize continuous terrain, cartographers had to invent a new geometry. The solution is the contour line. A contour is a strict mathematical boundary that connects all contiguous points of equal elevation. The entire system rests on a single geometric rule: the vertical distance between any two adjacent lines, the vertical interval, must be absolutely constant. Imagine a 3D landform. Now intersect that landform with perfectly flat horizontal planes at regular, measured vertical intervals. By taking the perimeter of each horizontal slice and projecting it straight down onto a flat surface below, we compress the three-dimensional volume into 2 dimensions. Viewed from directly above, the result is a set of flat, concentric rings. The physical z-axis is gone, but the elevation data is perfectly preserved in the geometry of the circles. Looking at this standard textbook diagram, we see the exact same logic applied. Figure 1.6 proves how slicing the physical cone translates directly into the circular topographical map. A modern topographical map is a highly compressed, top-down projection of stacked data planes. Because the vertical distance between slices is locked, the horizontal distance between lines becomes a direct mathematical readout of the slope. This figure breaks down the visual signature of terrain. On the left side, labeled A, the contour lines are drawn far apart. That wide horizontal spacing indicates a gentle slope. You walk a long forward distance to gain little vertical height. On the right side, labeled B, the lines are packed tightly together. Minimal horizontal distance between the intervals means maximum vertical gain, a steep slope. When you combine these contrasting line densities on a single landform, you can instantly identify complex asymmetrical geology. Take a look at this diagram of a watershed ridge. The western side shows tightly packed contours, the steep, scarp slope. The eastern side has widely spaced lines, the gentle dip slope. The line spacing alone defines the physical asymmetry. The geometry also works in reverse. What does it mean when contour lines stop entirely, leaving a blank void in the center of a landform? This chart of a plateau provides the answer.
The dense rings indicate steep sides rising up from the lowlands, but the wide, empty gap in the center represents flat terrain at high elevation. By reading the horizontal density of the lines, a trained surveyor mentally extrudes the flat page back into a rugged, three-dimensional landscape. If wide lines mean flat ground and tight lines mean steep ground, what happens when the terrain is perfectly vertical? A vertical surface covers multiple elevation intervals without moving forward horizontally. Therefore, on a top-down projection, the lines visually collapse into each other. This diagram of a cliff shows the anomaly perfectly. Look at the coast. 3 distinct elevation contours converge into a single thick line. That convergence is the absolute signature of a shear drop. You can apply this exact same geometric logic to river systems to spot impassable hazards. In this topographical rendering of a waterfall, you can see the blue line of the river crossing the terrain. The V-shaped contour lines merge directly across the water's path, perfectly encoding a sudden vertical drop in the riverbed. The geometric anomalies on the page identify sheer drops and fatal barriers with mathematical certainty. Topographical data dictates the path of human infrastructure. When planning a transcontinental railroad or a highway, engineers don't focus on the high peaks. They scan the map for specific low-elevation contour patterns that indicate breaks in a mountain range. This diagram shows a pass. Notice the wide spreading of the contour lines stretching horizontally between the 2 circular peaks. That gap is a traversable route with manageable grades. Contrast that with this figure of a col. The drop between the 2 peaks is much sharper and occurs at a higher altitude, making it a far more difficult route to engineer. Because building directly over a steep gradient is economically and physically prohibitive, these geometric gaps become absolute, non-negotiable bottlenecks. Roads, railways, and communication lines are funneled exactly through these precise topographic corridors. The map's negative space, the areas where lines spread apart to form passes and saddles, serves as the foundational blueprint for how civilizations connect to one another. Because our major infrastructure is strictly bound by topography, human settlements form predictable geometries in response. Linear settlements grow like vines along the paths of least resistance. You find them strung tightly alongside river valleys or low-grade cart tracks. Where these topographic corridors intersect on flat, highly connected terrain, settlements swell rapidly into dense clusters. Where tight, restrictive contour lines dominate the map, human habitation is forced into isolated, scattered pockets. This survey map shows the correlation between geology and human activity. Red squares indicate permanent settlements. Notice how these artificial blocks strictly obey the borders created by the brown geological contour lines. They avoid the dense gradients completely, pooling within the white flat spaces. A topographical map is a geometric record of physical reality. It encodes the unyielding shape of the Earth and rules governing how humanity inhabits the landscape.